Hi everyone, and welcome to Eric's Electronics Workbench. The project on the bench today is this US military UGC-74 communications terminal. These terminals were often used in radio teletype systems, but can be connected to other computers and devices, or even directly to each other. The I/O can be set up for a variety of different interfaces and protocols, such as 20 or 60 milliamp loops, low-level data, NRZ or diphase, ASCII, or Bodo. The UGC-74 in its transit case weighs in at a back-straining 100 pounds. Now I've already removed this machine from its case, but it's still extremely heavy. The build quality is absolutely incredible. Now there are three versions of the UGC-74, A, B, and C. This machine started as version A, which uses the rotary drum printer, but was modified by the military in 6 of 91 to version B, which has a dot matrix printer. Now the C version is also a dot matrix printer, but adds an external removable memory module and some other minor additional features. The memory module used what's known as magnetic bubble memory, which is a technology from the 1970s, was obsolete by the late 80s. The UGC-74 is also known for its use on early space shuttle missions. NASA heavily modified the A version for use on the space shuttle as they needed a very reliable teleprinter and had ruled out using electrostatic and thermal paper printers due to flammability and other concerns. Even the canary yellow paper in the UGC-74 required a special waiver to be used on board the shuttle. So the problem with this UGC-74 is that the printer doesn't work. So let's take a closer look. Alright, so here's the printer, at least what we can see of it with the front panel open. So this panel is normally closed like this, and then this latch here and over here just holds things in place. And this front panel could open further, except it's bumping against this front edge of the workbench right now. So I'll put a picture up on the screen of what's on the inside of the panel. You can see the wiring that connects to the switches and indicators, and it's part of this harness over here. So here's the print head, the dot matrix printer. So it actually moves very easily, and it makes kind of an odd sound, but it is normal. So I know that sounds a little bit unusual perhaps, but it is moving very easily. Now there's a motor right here with a cog belt. So there's a belt there, and it goes around this pulley to the other side. So this is the drive motor that's moving this back and forth. And in actual operation, this would be moving quite rapidly back and forth. That's why there's a cog belt. They don't want it to slip at all. There's a little, like a shutter that extends off the side of this, and it goes over to an infrared sensor. So when this is all the way over like that, that's the home position. It's able to detect that. So again, it's like a little piece of metal that sticks out on the side right there, and it goes between the transmitter and receiver. It's an infrared sensor on the side over there. But at any rate, this moves very easily. This is the ribbon, so you can see how it goes into this cartridge right here. And so there's a one-way clutch, and that's what you're hearing make that odd sound, that clicking. So when I go this direction, the ribbon is being moved around, and then I go the other way, it doesn't move it. If it was linked all the time to this motor, the ribbon would just rotate back and forth. They want the ribbon to continuously go around, so it can only move the ribbon in one direction. So all of that's, easily moving. There's nothing mechanically jamming up. Again, the motor rotates very easily because I can push or pull this. So now let me power it up and watch what happens. So turn on the power here. It's 120 volts. So I'll turn this on. So when I turn this on, it should go into that startup mode where it's printing out the confirmation and the configuration and so forth. Uh-oh, that doesn't sound good. Nothing's happening. Might see a reflection down here from the copy lights. Yeah, so we got an alarm and things are going off there. Not good. So obviously the power is on, and things start to come to life a little bit, but this absolutely doesn't move. And it makes some very strange sounds, and then you might have heard a beep, a tone there, and that's a speaker that's over in this corner. That's the alarm, because it's detecting that this isn't moving at all. It's not getting a response. Now, here's the thing. I'm going to turn this back on again, and remember, this moves, no problem, but watch this. I can't move it. It's absolutely locked. Look at that. Turn it back off again. No problem. So it looks to me like an electrical problem, but it's almost like the motor's trying to drive in two directions at once. And I'm not sure if it picked up on the microphone, but there's kind of an odd, almost a whining sound that's coming from the motor. So I don't think the motor is just being driven by a simple, like direct current, let's say 12 volts or something like that. It's probably a pulse width modulation or something like that going into this motor. I think it's a little bit more complex of a drive system that they're using, because again, it makes kind of a whining sound, and almost like a servo motor or a stepper motor or something like that. But something's not right, because it absolutely locks up, and I can't move this when the power is turned on. Now, if I move this all the way over to the home position, so now it's going to block that shutter. It knows it's in the home position, and I don't think this paper was moving before, but with it in the home position, I think the paper might move when I initially tried it. So let's see if that does it again here. Yeah, see the paper just moved now. So a little bit different response. I move that over and turn it on. Yeah, see, the paper didn't move now. It didn't do a line feed. The alarm goes off again. Oh, it did a line feed there. Yeah, I'm not exactly sure what's going on, but definitely a problem. And again, because it printed out here, it's like it just suddenly failed, because it did a printout and then now it doesn't work. So something just suddenly failed from the last time it was turned on to, basically when I tried it here, the other day and saw that it didn't work. I have another one of these machines in my collection that works. It's the B version. The circuit boards that are, let me just move the camera up here again. These boards over here, very, very easy to get to. You just open this cover up and take these boards out. And I think it would be worth taking those boards out of that working machine and putting them into this machine, one board at a time, and see if it takes care of the problem. Because I believe one of these boards is related to the printer. But there's also some other circuitry elsewhere in here that is also part of the printer. And that's much harder to get to. But these boards would certainly be a starting point. The main microprocessor, for one thing, maybe something is terribly corrupted in the ROM or something like that. If that's the case, it's really not repairable, unless I could get another set of boards or something like that. Would be kind of a remote chance, but it might be able to isolate down a problem to a board at any rate. And if changing these boards out doesn't have any effect, well, at least we could rule them out and start looking elsewhere. All right, so here's another UGC-74B. So this is the same version, same type of dot matrix printer as the machine that I'm trying to repair, but this machine works correctly. So I'll turn it on and you'll see how the printer is supposed to work. You'll be able to see the print head moving back and forth. So here we go. Takes a moment to start up. All right, so you can see how the printer is supposed to operate. So I'll go ahead and pull the circuit cards that are along the right-hand edge out, and I'll replace them one at a time in the machine that I'm trying to repair, and let's see if it makes any difference. All right, so I swapped out this first board. This is a print control circuit board. Now there is additional circuitry that controls the printer. Some of it's located in this corner, and additional circuitry down underneath the printer. But this is a good first place to start. It's certainly easy to access. This circuit board right here is out of the machine that's not cooperating. Just a little bit closer here and you can see the board looks perfectly fine. There's no visible damage. So let's see if swapping out this board made any difference in how it's operating. All right, here we go. No, unfortunately not. It's not moving. Yeah, no change at all. That's unfortunate. Well, I'll go to the next circuit board. This middle circuit board over here, turn that off again, is for the communications interface. So I don't think that board would have any effect on the printer, but you never know. So I'll go ahead and get that swapped out. Let's see what happens. All right, the next board is swapped out. And here's the board out of the machine that's not working properly. Again, visually it looks perfectly fine. These boards have a very shiny look to them because they're conformal coated. All right, so let's see if changing that board out has any effect. All right, here we go. No, unfortunately not. Still making the same sound. The print head's not moving. So let's try the next board. All right, so I swapped out the microprocessor board. So here's the board out of the machine that's not working correctly. So I don't see any visible damage on the board. All right, so I'll just set the board back here, and let's see what happens. Here we go. No, unfortunately no change. Still making that odd sound. The carriage isn't moving back and forth. Yeah, no change whatsoever. Oh, a line feed. Paper just came out a little bit. Yeah, shut that down again. Yeah, no change at all. So you can safely rule out this group of circuit boards, because when this group of boards were installed in the other machine, that machine works perfectly fine. So the boards originally in this machine have no problems because there's absolutely no change. So I think it's time to start taking a look at some of the other electronics related to the printer. So there's some electronics in this corner. I believe what's up in this corner is related to the driver for the carriage motor, so that's definitely of interest. And there's a rather large circuit board that's underneath the print mechanism. I need to take a look at that as well. All right, so after removing a handful of screws and other hardware, I was able to get the printer assembly out. So of course it fits in this area right here. And this is turned around backwards right now, so normally the paper roll fits right here, that roll right back there. And I was looking at the printer and thinking about what could actually be tested on it. And after looking at the service manual, I realized that this circuit board right up on the top right there, which normally has this cover acting like a heat sink right on top of it, well, that circuit board is the driver and the control for the carriage motor. And this wiring right here goes down to the motor. So this circuit board right here is actually known as the carriage motor current control circuit card. I thought that would be a good place to start testing, given that that motor isn't moving and working the way that it's supposed to. And there's certainly easy access to the components up on the board there. So the only way to really test that, because there's so many different logic signals and control signals and power supply voltages and so on, is to have this plugged into the main controls and circuit boards over here. And luckily you can do that because the wiring that comes off the side right here goes into two plugs, and there's just enough wiring to reach back over, so when this is positioned over here, this wiring can plug back into the motherboard right there. I have this propped up on a screwdriver like that. Everything just reaches. And then over here, there's these two wires, and these two wires go to terminal studs right over that corner, so I just have some long test leads connecting things back together again. Now there's no problem in testing this without the paper roll installed, because the way this knows when the paper roll is actually out of paper is that the end of the paper on that roll is attached to the tube in the center. I tip this here, you can just see there's a hollow tube, and then it has a piece in the center with a bearing on each end right now, like a rod that goes through it. But anyways, that paper attaches to the cardboard tube so that when it runs out of paper, the paper pulls tight and it causes this bar to pull down, and there's a switch. You can hear that click right there? And then that's what tells the printer that you're actually out of paper. But if this bar is up, then not having any paper in here won't affect the printer actually trying to do something. And there's another paper low sensor, which is actually over there still, and this capacitor had to be removed, part of the disassembly, and I have it sitting on that lever right now, just kind of pressing it down. So it thinks there's paper in the printer, and that's not going to keep things from functioning the way they're supposed to. Now, of course, if it tried to print, you don't want that to happen because you don't want the print head to print on the rubber roller down in there. But it's not trying to print at this point anyways. So going back to the circuit board right here, let's take a look at the schematic, and I'll show you what I've measured so far and what seems to be present and correct and what's actually missing. And let me just move the camera over a little bit. One other thing just to point out about testing this. You can see I have my Fluke scope meter. And the reason I need to use the scope meter is because the circuit common in this circuitry on this board and throughout the printer, the common is not the same as ground, like chassis ground or earth ground. So if you have a traditional oscilloscope that's earth grounded and you connect it into what is a better term is circuit common, because again, it's not really a ground point in here, you would cause big problems because it's not meant to be referenced to earth ground. So you need to use an isolated oscilloscope, exactly like this fluke scope meter. And I can't really use the traditional probe that would go on the fluke scope meter because this board is conformal coated. So I have to use these two probes right here, very, very sharp points on the end to kind of pierce through that conformal coating. But it works well because the signals that I'm measuring aren't extremely high frequency, so you don't have to have shielded cables and like a traditional probe. The regular probe that goes on that scope meter has an alligator clip for the ground side, or again, you could refer to it as circuit common, but there's no way to even clip that into this circuit. So those needle sharp test probes like this work very well for this application. All right, let's check out the schematic and I'll show you what I found so far. All right, so here's the schematic for the carriage motor current control board. So over here we have phases A, B, C, and D. Now the order that these phases sequence through determines the direction of rotation on the carriage motor, which is also a four-phase motor. And that motor is shown over here. Now the motor would have four windings, but only one is shown for simplicity. So one side of each winding attaches to a positive 53 volts. The other side of each winding attaches to these lines up here. I'll talk more about this in just a moment. Now these phase signals are originating from the print control board, and that's one of the circuit boards that I swapped out earlier in the video, and it had no effect on the problem. Now I went ahead and measured these phase signals, and they look perfectly fine, no issue whatsoever. All four are present, and the waveforms look good, which again makes sense because changing this board didn't have any effect on the problem that we're seeing. Now the phase signals are coming into U2, which is an inverter. And a convenient place to measure them is just on the input side of the inverter, so 13, 11, 3, and 9. And again, the pin 7 you can see goes to the ground or the circuit common, but again, it's not the same as earth ground or chassis ground. Now you can see on these data lines coming in here that all four of them go up to these 10 k ohm resistors, and then the other side of the resistors goes to positive 5 volts. These are known as pull-up resistors, so essentially it's pulling these data lines up to 5 volts. On the print control board over here, there's circuitry that pulls these lines down to essentially 0 volts, so these lines are just switching between 0 and 5 volts. Now the output of these inverters goes over here, all four are the same, come up to these lines, comes over across to the gates on these power FETs. So these power FETs are acting like switches. So just looking at this one, for example, you have positive 53 volts through the motor winding over here to the drain on the FET. When it's on, very low resistance between drain and source. So we have a path down this way, comes over here. Very low value resistor, 1.47 ohms, 3 watt rating. So it comes over here and down to the circuit common. Again, this circuit common is not the same as ground or chassis ground. Now, this resistor develops a little bit of voltage across it as a current flows through it. So what they're doing is just monitoring the current that's flowing through the motor winding, and that is picked off right here. It goes down as the current sense, feedback number 2. Same thing happens over here, feedback number 1. And you can see that they've grouped these two FETs together because the sources are tied together and come down this way, and these two are tied together and come down over here. Now I measured these resistors and voltages, and everything is looking okay over here. Now if we go back over to this side, you can see the outputs of this inverter. So again, with the inverter, you have an input that's high, output is low. If the input is low, then the output is high. If you go down this way, we have 1.78k resistors, and the other sides are all tied together. It says positive 26 volts, but there's a Zener diode. This Zener diode is regulating this down to a lower voltage. It's about 12 or 13 volts. So this must be current limited, because if it wasn't, this would act like a direct short coming down here. It would conduct very heavily. So this is just making a simple voltage regulator, but there's more to this power supply. They're just not showing it here. It must be on another circuit board. Now it looks to me like what happens is you have a higher voltage here, and the gates on these FETs has a very high resistance. A very low current would flow. So essentially, you have very low voltage drop across these resistors. Now, when these inverters go low, I believe they're able to sink current. So they would pull the line down low, but when they let the line go high on the output, then this higher voltage is able to come up here and drive the gates on these FETs. So it looks like what they're doing is basically just driving these with a little bit higher voltage, not just the 5 volts over here. Now where I noticed a problem is that this line here and this line right here are not switching the way they're supposed to. This line is stuck high all the time, and this line is stuck low all the time. Now these are supposed to be pulse width modulated signals. And this pulse width modulation is related to this current sensing that happens over here. So essentially they're generating the pulse width modulation signal and regulating the amount of current that can flow through the motor winding. But because this is stuck high and this is stuck low, the switching is not happening the way it's supposed to in these FETs. So I need to go back to see why these lines are not switching correctly, and this signal is originating on the circuit board that's underneath the printer. So I need to remove that and see what's going on there. There was a piece of specialized test equipment that the military used for testing that board, and you're able to plug the board in, and the tech manual references it. And it basically is like a simulator, and you could power up the board and simulate it being in a printer, but of course I don't have any of that test equipment. So I'll have to see what I can do for the troubleshooting on that board, taking a closer look at it. Now I suppose that this inverter up here, U4, could possibly have a problem that's holding the data line, or this input line right here, high, and this one is being held low. Maybe something with U4 is going on, but I really don't think so. I think the problem is actually on this other board. Now up here, this circuitry, you see these diodes right here. These are steering diodes, and the whole purpose of the circuitry up here is to suppress or clamp the kickback voltage that occurs in the motor when the windings are switched off. All right, so let me take a look at the circuit board under the printer. I need to look in the tech manual and see how to even remove that circuit board, get it pulled out, start taking a closer look at that circuitry and that schematic. And so after removing some more screws and hardware, I was able to get this circuit board out from underneath the printer, so it slides out of this slot right here. So there are a number of things going on the circuit board. So there's a power supply. A lot of the power components are along this edge. So there's some power FETs under this heatsink, some rectifier diodes under this bracket acting like a heatsink. These two devices are transformers. I think there's some control circuitry right here for the power supply. So it's a switch mode type power supply, and it's generating a number of different voltages to operate the printer. And some of the voltages are over 50 volts. So if you're following along, you're definitely doing so at your own risk. Take care and be safe, because voltages over 50 volts definitely pose a shock hazard. Now over here you can see there's a connector. This goes off to the print head. So the circuitry in this area is related to the dot firing on the dot matrix printer. There's two integrated circuits here. They're both identical. This one might be a little bit hard to see on camera, but these are PWM controllers. They're SG1524s. And previously on the other circuit board where I mentioned those two pulse width modulation lines weren't changing, those originate off of these chips. So I'm definitely interested in doing some testing and looking around this area here. Now there's some other circuitry going on over here that's related to external sensors on the printer. And one of the first things that I wanted to try to do is power up this board, because if you can't power it up, it's very hard to test it. You can test passive components, but that will only get you so far. So for example, on these PWM control chips, there's an oscillator, and I was wondering, is that oscillator running? And tests like that can only be done if things are powered up. So I found the schematic that shows this circuit board in the test set, which is basically a simulator to allow this board to be powered up. Now again, I don't have any of that kind of test equipment, but looking at that schematic, and I'll show you the schematic in just a moment, I was curious, how do they actually power up the board? And it turns out that it looks like it only requires 26 volts DC and 8.6 volts DC. So 26 volts coming in right here, 8.6 volts over here. And with those two voltages, this should come to life. Now what I don't know, and it's not talked about, is how does this power supply react if there's no load connected? So there is some load for the components that are on this board, but things like the carriage motor and other devices aren't even connected. Would that affect the power supply operating, or what if there's no load at all? Will it still work properly? And that's not talked about, because in the simulator they actually have a carriage motor and other things all connected to this. But there's some external switches and things like that that you can manipulate the print head and firing the dots and things like that, and status lights and so forth. All right, so here's the schematic for the test fixture for the print drive board. So this is the circuit board we were just looking at. So you have connector P1, P2, they appear over here as well, and then J3. So J3 is going off to the print head. A lot of circuitry going on here, a lot of interface going in and out of this circuit board. So this is the stepper motor, that's the carriage motor. This is the carriage motor current control board that we saw earlier in the video. But I was interested in how is this being powered up. So the only external power that's coming into all of this to operate it is down here, these two lines. This is a 26 volt input. If you follow this top line, it comes up here, it says 26 volts unregulated. It goes into position number 2 on P2. And then the return is down here, the negative, and that's right here on number 7. And right here is the 8.6 volts coming in. So you have 8.6 volts on, it looks like that was number 7, and the return is on number 2, and that's on connector P1. So over here, there's a lot of circuitry that's part of the simulation for this test set. Some status lights and some switches and things going on up here. A lot of switches right here to, exercise and activate the print head. So, we don't really care about any of that. I just want to be able to power up this board. And again, it looks like there's just the 2 external voltages that are required to bring this thing to life. So I've been studying the schematics to get a better understanding of how the circuits work on this board, and I've noticed a couple things. So just a correction to something I mentioned earlier, but this area over here, this heatsink, has a bunch of power FETs under it, and they're not related to the power supply. They're for the dot drivers on the dot matrix print head. So the power supply is from this point over to this area here. So there's 3 power FETs under this heatsink and 3 under this heatsink. Those are for driving these transformers. Now I also noticed that the regulated 26 volts that makes its way around on this board, it also comes off to these connectors for some external circuits, but that 26 volts was very low. It was about 19 volts, so that didn't seem quite right. And I started looking at the schematic for the power supply section and thinking about maybe it needs a minimum load. Now loading down the 26 volts even further didn't help anything, it just falls away. But I noticed on the power supply they're actually regulating the 53 volt tap on the transformer that also provides the 26 volts. And when I saw that the regulation point was coming off of the 53 volt tap, I thought, you know what, I bet if you load down the 53 volt output, it'll cause the 26 volt output to actually rise up, and that's exactly what happens. So it does need basically a minimum load on the 53 volt output. And it turns out that a 3000 ohm resistive load on that 53 volt output seems to be about right for bringing up the 26 volt line to its normal operating voltage. So I'll show you that right now. So let me turn this on here. The convenient test point is on this capacitor over here. So I'll just show you the negative probe right here. I'm just touching over on a common point on my test leads to the side. And if I go to this capacitor right here, touch right there, there it goes. It's not making a good enough connection. There's a conformal coating on everything. There it goes. So you can see 26.23 volts. Perfect. That looks very good. Now I'm going to disconnect that minimum load that I have. So the 3000 ohm resistor. So I just disconnected it right there. So if I go back over here again, now look at the 26 volt supply. See, it's dropped down 19.5, 19.6. So that minimum load kind of requirement seems to have to be in place to make the power supply regulate correctly. So all the voltages do look correct now in this circuit. So I'm just going to connect it back together again here, like that on that resistor. So again, it's a 3000 ohm power resistor that I'm using. So let's go over to the schematic and I'll show you what's going on with the power supply and why that minimum load is required. Here's the schematic for the power supply portion of that circuit board. So this power supply generates a number of different DC voltages for use by the printer. Now starting in this corner, these are the 2 input voltages. So this says 26 volts unregulated and then 8.6 volts. So this says unregulated to denote it from this output over here, which is 26 volts regulated. But back over here, the 8.6 volts comes in, there's a Zener diode, and this drops the voltage down to 5 volts. So a very simple voltage regulator, and this 5 volts is distributed off to numerous other places on the board. Now this 26 volts DC input comes over here. You can see the path goes 2 ways. If you go down this way, it goes into some support circuitry for this PWM chip, and same thing down here. If you follow the path over this way, it comes down to the primary winding on this transformer, and also to the primary winding on this transformer. Now the other side of the primary winding comes over here to these 3 power FETs, so it's connected to the drain on each of these FETs. These are in parallel for load sharing. And the same thing down here, just coming over to each of those FETs. Now these FETs act like a switch. So when they turn on, there's a very low resistance from the drain to the source, and they're controlled by the gate. So you can see all three gates are tied together. It comes over here to this PWM chip. So the path comes from this transformer winding on the primary side over to each of the drains on the FETs. Low resistance path to the source. The sources are all tied together. Comes down this way to these very low value resistors for current monitoring. And on the other side of those resistors, it goes to circuit common. So the same thing happens down here, but there's no low value resistors for current monitoring in this portion of the circuit. So this switching is happening at a very high frequency, so it allows these two transformers to be physically quite small, which of course is typical in a switch mode power supply. That's the whole advantage, is that these transformers can be made physically small because as the switching frequency goes up higher and higher, there's less iron needed in the core of the transformer. Now on the secondaries of each of these transformers, you can see there's multiple taps. One end just ties to the circuit common on each of the transformers. And there's a very simple half-wave rectification. So you see a diode there, a diode, another diode, and the same thing here, diode there and right there. And then there's filtering with some capacitors. Now over here, you can see the output voltages are listed down this side. So we have positive 68 volts DC, positive 53 volts, positive 26 volts, positive 63 volts, and then positive 48 volts. Now on this positive 48 volts, right here it says shunt C and shunt B. So there's an external power transistor that's used. So this is the collector and the base. The emitter is connected elsewhere. And I don't have that transistor connected in the circuit, but it doesn't matter because this 48 volts is used to fire the dots in the dot matrix print head, and we're not concerned about that anyways, so I don't need to complete this part of the circuit over here. But I did measure all of these voltages, and they look great now, especially with that minimum load connected. So this 48 volts is actually very close to that even without this shunt regulator. It's actually just a little bit higher than 48 volts, which to be expected because then they are regulating it down. Now up here, if you take a look, here's the 26 volts DC that should be regulated. It was quite low. Now on this output right here, it says 53 volts regulated. If we go back here, there's a path that comes down here, comes over here, and comes up into this circuit and this PWM control chip. And when I saw that, I thought, you know what? They're regulating this 53 volt output. So if you load this down, this is going to compensate for that. It's going to drive this transformer harder to keep this voltage where it should be. But when it drives this transformer harder, it ends up causing the other voltages to rise up. So the 68 volt output and this 26 volt output. And it definitely made it go up. It was about 19 volts. And then as you saw with that test that I did, it came up to 26 volts. So it definitely has to have that minimum load, and without it, this falls away, it's too low. Now, of course, this power supply is application specific. This isn't some power supply, it was just a general purpose supply, and they're hoping that you're going to make it work. This was all specifically designed for this printer. So in actual use, the loads that are connected never changed. It was very predictable. So it's not surprising that it would require a minimum load because, everything is connected. It's always going to have the specific loads on the power supply. So I think I have a better understanding of how this works, and I can test it now that the voltages are correct. Well, it looks like I was on the verge of seeing the magic smoke come out of this UGC-74. So things are falling apart faster than I can fix them. So when the problem occurred, I was using my scope meter to check the signals on this carriage motor control board. And I had my scope meter connected into the circuit common on this board. So there's a capacitor that has one side connected to circuit common. So that side of the capacitor makes a convenient point to connect the negative test lead to. And I'm absolutely certain that that test lead didn't touch something that it shouldn't have and cause a short circuit. And then I was using the scope probe and checking around on the board. And I know for a fact that I didn't slip and touch something that shouldn't have been touched and cause a short circuit or any problems like that. And of course, the scope meter is isolated, so it could connect to any part of the circuit. It's not going to interfere and cause any issues. So again, the scope meter is the only thing that was actually connected into the circuitry. And the way that this is set up here is exactly how I have had it before when I was testing it. So the printer is plugged into the motherboard over here. These two test leads are connecting the wiring on the printer over to the terminals that they normally connect to. And these test leads didn't short out, no problems on the alligator clips on the ends. And with the problem that this printer is having, the power has to be cycled on and off. I can't just leave the power turned on, the carriage motor just sitting there stalled out and kind of humming away with the excessive current going through the windings and end up damaging the motor. So when I was doing the testing, again, cycling the power on and off as needed, I reached over here to turn the power back on when I was ready to take the next measurement. And right now the line cord's unplugged. When I turned the switch on, I saw the lights on the front panel flash quickly and then just turn off. Okay, that didn't seem right. So I turned the switch back off. I waited 5 or 10 seconds, turned the switch back on, and it was just completely dead. Nothing happened. So I turned the switch back off again, and I checked these fuses, and one of the fuses was blown. I didn't like seeing that because these fuses are right on the main line coming in. So depending on if you're using 120 volts or 240 volts or 28 volts, these fuses are sized differently depending on that voltage. The current needs to be changed. And that's why these spare fuses are put up here. And you can see probably from prior time in the video, 2 fuses are now missing because, well, I've blown some more fuses. I changed them out and that didn't do anything, didn't help. So now I have several fuses that have been blown and will have to be replaced. So definitely a problem going on somewhere in here, maybe in this module or possibly over in this module, or maybe even in the power supply down in the bottom. Now, the power supply that makes all the voltages that distribute around in the UGC-74, I think they're current limited and have protection. I really don't see any other fuses in the unit. But again, these fuses right here are on the main line coming in. So the fact that those blew really means a major problem has happened somewhere right on the input, I would think, or maybe on an input down on that bottom board on the main power supply. Now, I looked at the schematic, and the main AC line comes in and it goes to a transformer. I think the transformer is over here. It might be in this module, but I believe it's over here. And there's also a bridge rectifier, and that off the bridge rectifier is an unregulated DC voltage, which again, if I understand correctly, it's coming over to these terminals and can be checked there, but it goes elsewhere down to the power supply on the bottom. So I've been testing components in the power supply and the power entrance circuits, and I can't find anything wrong. In fact, I put new fuses in, and now the UGC-74 powers up, and it no longer blows the fuses. So I'm really not sure what the problem was, but I wanted to look inside this module. So this is the interface module that fits in the back of the unit. Switches along that top edge and the fuse holders right here. And I just wanted to visually inspect inside of this module, and I did notice 2 things, and I'll show you that in just a second. Now this section right here is part of the power supply, and I was able to verify that these circuits are working okay just by externally measuring how they're performing, but again, I wanted to visually inspect inside of here. So just looking at the schematic again. So I verified that the bridge rectifier is okay. This transformer has no issues. These TVSs are okay. Just the general wiring and how the circuits are measuring is checking out perfectly fine. There's a lot of feed-through capacitors around various places. All of them are checking out okay. This common mode filter or inductor right there is testing okay. No problems with that. That common mode inductor is this part right here. So again, I'm not seeing any problems in the circuit, and when I powered it up, the voltages check out okay. It's right at 26 volts over here when it's loaded down by the other circuits that are in the UGC-74. Now in this module, what I noticed is, I could just zoom back out a little bit here, but this is the cover that fits on here. And you notice this dark kind of a stain right here? So when this is installed, it fits in here like this. So if we open this up, that stain right here would be right in this area when this fits down. And that would be this common mode filter. And there's some terminals on the top, basically pins that stick up that the wires are soldered to. And I don't quite like how close those are to the cover. If I get this tipped a little bit here, I think you can see kind of a side profile. Those pins, get this zoomed in again a little bit closer here. See how close those pins are to this top cover? I mean, when I tip that down and you sight from this side down to the other side, they're extremely close to this cover. Well, if those were to touch the cover, of course the cover is earth grounded, and that would cause a short circuit and would certainly blow the fuses. And this kind of dark area right there, to me that certainly looks like something was hot or had arced against that. Doesn't really look pitted, but definitely a stain on there. I'm not sure what was going on there. Now maybe that's an old failure and perhaps this has been replaced. I do notice that these numbers have been etched in here, and that really doesn't look like something that would be on mil-spec components. So I think someone has been in here and etched those numbers in and maybe was desoldering some wires and doing some repairs. But that's really the only thing in here that looks like it's ever been touched. Everything else really looks original. Definitely a lot going on in this module. But the other thing that I noticed is down here in this connector, right here, I'm going to try and point to it, and I'll put a photo up on the screen that's a little bit closer as well, but if you look right between the yellow and green wires, right here, there is a piece of solder that's sort of wedged in there or melted and fell in there. Perhaps someone was doing some repairs in this area and it dropped down into here. I'm just wondering if that piece of solder is bridging those two wires together and was causing a problem that was intermittent, and maybe it arced and kind of cleared itself a little bit. So if we look, I think it's 4 and 5. Let's see, that 1, 2, 3, yeah, 4. I think it's numbers 4 and 5, or positions 4 and 5 on there. Grab the schematic again. So number 4 and 5 over here. Here's, I'm not sure this is on the, you can see that there. There's 4 and 5. Did they skip 5? No, 5 is up here. It's not in numeric order. Okay, so here's 4, and then 5 is up on the top. So that would be, well, that's AC line going to the primary side on the transformer. And number 5, it's that center tap that's used in the DC power input. It really wouldn't go anywhere over here. There's a feed-through capacitor. Certainly, if that had AC line voltage, though, I would expect this TVS to fire and conduct, and then you'd go to chassis ground. That's a problem. That would definitely cause a short circuit. So maybe that's what was happening. You know, maybe that solder bridge was causing some intermittent short circuit there. So I'll get in here and I'll just remove that solder, and I haven't even touched it yet. I don't know if I can just kind of pick it out or if it's actually melted in there, and I'll need to kind of, desolder it basically. But these terminals inside this connector down here, it's touched up on there for you. Those are crimp connectors. It's not supposed to be soldered, so there shouldn't be any solder in this area. So I think that just fell down in there. Again, it looks like maybe some work was being done here. So the little piece of solder has been removed, and it had adhered quite tightly to the terminal, so it wasn't just loose and rolling around in there. Also, I'm going to trim these 4 terminals that are on this common mode choke just to get them down away from the cover. They're way too close in there. So then I'll get everything put back together. Hopefully this fuse blowing problem is taken care of, and then I'll continue with the troubleshooting on the printer. So I've been trying to figure out why the 2 PWM signal lines that I talked about measuring earlier in the video are stuck and they never change. One is always high and one is always low. Now those PWM signal lines originate on the large circuit board that's below the printer, so that's what led me back to testing things on that board. And there's 2 PWM control chips, and it seems odd that both chips would fail. You can always have multiple component failures, but again, it just seems odd to have both of those controller chips fail at the same time. So I was looking at something that might be common in the circuit that could cause the whole circuit to go dead and not perform correctly. I really wasn't seeing anything on that board that would do that, and all the circuits and the components that I was measuring were testing out okay. So I thought, well, I need to take a closer look back on this board again and see if there's something going on here. Now, what's a little bit tricky to measure on this PWM signal and just the circuit in general is because the PWM signal is to control the current that's going to the carriage motor. And there's a sensing circuit on here that I already talked about. It has a feedback signal that goes to this other circuit board, and it controls that PWM signal. So it's essentially a loop that's going around, and loops are notoriously difficult to test because a problem can show up anywhere around that loop. You know, the whole circuit doesn't perform correctly, but again, it's just one component that can take down that whole loop. So sometimes you have to break the loop to really isolate the problem. Well, let me show you what I found on this board, because it really looks like there is a problem over here. So I'll get you zoomed in a little closer, show you the digital multimeter, take some measurements, and I'll show you what's going on. So these 4 power FETs are controlling the current through the carriage motor windings, so the 4 phases of that motor. So just taking a look at the schematic. So here are those 4 FETs. And these are enhancement mode types of FETs, meaning that they're in the off state when you have a 0 gate to source voltage. So in other words, a very high resistance between drain and source when you have 0 gate to source voltage. Now compare that to a depletion mode FET that's in the on state, or a very low resistance between drain and source when you have 0 gate to source voltage. Now how can you tell the difference on a schematic between enhancement and depletion mode FETs? Well, again, these are enhancement mode, and you can see they're drawn with this dashed line between drain and source. So that reminds you that you have that open or high resistance between drain and source with 0 gate to source voltage. But the depletion mode would be drawn with a solid line between drain and source, and that reminds you that you have that low resistance path when you have the 0 gate to source voltage. So when we take some measurements in this circuit, these FETs should look like open circuits, and the only resistances we might see would be other components around the circuit. So gate to source, gate to drain, drain to source, all very high resistances. So I'm just going to use my digital multimeter in the resistance mode just to measure around these FETs, and I'll show you what I found. So I'm not trying to actually measure a particular FET for an operation and see that it's working. I'm just looking for resistances in the circuit that are way out of tolerance. So something that looks way too low, like a short circuit, okay? Also, these devices might look a little bit odd on here. It's sort of this donut shape with the hole in the middle. These are just heat sinks that are clipped onto the metal cans of these devices, and the center of that hole is threaded. There's a plate that goes on here for a heat sink. All right, so let's take a look here on the other side. And on this board right here, I can see that, let's get this tangled up here. So we've got the traces right here for each of the FETs across there. And the center pin on each of the FETs must be the gate, because it goes up here to the inverter, and that's the gate drive side of the circuit. So I'm not sure the drain and source which is which, but it doesn't matter for this test. I suspect this might be the source over on this side, that little square pad, but again, it doesn't matter for this testing. All right, so let's go like this here, starting on this first FET. I'll just go drain and source. So it looks like a very high resistance there, which is good. Other way around. There's a conformal coating on the board, so I have to probe in pretty hard on the board. But 3 megohms, so that's very high resistance there. That looks good. So I'll go gate to either drain or source. So 3.6 k ohms. So that's a lower resistance, but we'll check the other 3 FETs and we'll see if that resistance appears elsewhere, because it's basically the circuit 4 times. It repeats over. And then just going over here, looks like a very high resistance. Flip the polarity around there. 3.6, and on this side here, yeah, very high, 3 megohms there. Okay, so I wouldn't say there's any issues going on with that first FET. That lower k ohm range of resistance, again, we'll check to see if that appears elsewhere on the other FETs. So this FET here, oh, that doesn't look good. So about, what, 42 ohms right there? That's gate to either drain or source, but that's not looking good. The other side right there. Ooh, 126 ohms. Yeah, that's looking like it's shorted. Drain to source. Oh yeah, 86 ohms. So that FET's basically turned into a resistor all around between all its leads. So definitely a problem, it looks like, on this second FET right here. So let's go to this next one here. Looks like an open circuit between the drain and the source. Go up here to the gate. It's got high resistance there. Okay, there's that 3.6 k ohms again. So I think that's normal. I don't see any problems there. And the last FET right here. Not sure if that's getting a good connection there. Again, this conformal coating that's on the board here is kind of a pain. There it goes. Yeah, see, oh, there it goes. So 3.6 k ohms again. Yeah, so that resistance appears on these 3 other FETs, but on this FET right here, when I go to that same combination, 40 ohms, way too low, but this FET is very low resistance all around. And again, on this one, I think I already did this measurement across the drain and source. Yep, open there, that's good. And that 2.8 megohms, the other was about 3 megohms, so yeah, that looks fine. So of the 4 FETs, this second one in right here, to me looks like it's shorted. So that would be this one right here. So definitely looks like an issue going on there. I'm going to go ahead and pull this FET off the board and we'll just test it off circuit, because it's possible that there could be something else in the circuit that's making that FET look like it's defective when really the short circuit or the low resistance is elsewhere. I want to make sure that this FET is actually defective, so I'll just run it on a tester off the circuit. And it actually makes sense that if this FET is shorted and has that low resistance, that would be turning on that phase or that winding in the motor. And I think that's why that motor is locking up, because one of the phases is powered up all the time through this FET, which is just continuously on. And then of course the motor can't rotate. And then the PWM controllers are detecting the current that's always flowing and basically trying to shut that current down, but they can't do it because the FET isn't working right. So I think that's messing up those PWM control lines. All right, so the power FET is removed from the board. I pulled off the heatsink, and that heatsink was clipped onto that metal can extremely tight. And this little insulator fits under the FET to insulate it off of the board. So check this out. If I measure on the circuit board, right here, we go to this center pad, that was the gate. Go to this side right here. So that's an open circuit, looks good, looks good. The gate and drain, that looks like a capacitor charging up. Very high resistance there, way up in the megohm range. Go this direction here, no problems with that. Just flip the polarity around here, like that. Perfect. So I don't see anything else in that circuit that looks suspicious. All the readings seem to be very reasonable now, very high resistances. And I suspect that that resistance reading that we saw on the other 3 FETs that was in the several thousands of ohms is probably a protection diode inside each of those FETs. So that's perfectly normal. And again, this is in the resistance mode, not the diode check mode anyways. But check this out. If I take this little FET here and I can just go to the case. I think the drain is on this lead right here that goes to the case. So if I touch to the gate, that 123 ohms, so that's shorted, and drain to source, 83 ohms, which is exactly what we saw when it was installed in the circuit. So that's shorted. So this FET is completely toast. And I tried testing it on my component tester, and it couldn't even identify it. It's just completely destroyed at this point. Now with this heatsink removed, it revealed the part number on that FET. And now there's a complication. So the part is unobtainium. It's a very unusual part number. It doesn't turn up anywhere. So I think it's a special military part number. So stay tuned to see if I can find a solution and bring this UGC-74 back to life. So thank you for taking time to watch. And if you enjoyed this video, you can let me know by giving it a thumbs up. And if you're enjoying the content on this channel, please remember to subscribe, because there'll be many more videos coming up in the near future. You won't want to miss any of those. And don't forget to tap that bell symbol to be notified when I do post a new video. All right, until next time, take care. Goodbye for now.